The talk is about advanced HPIL communication. Be able to have several HP71B communicating with each other like in the network. So, okay, what is HPIL? HPIL is a low-cost, low-power, two-wire serial interface. It's in a ring, or a loop, and it was really a serial version of the HPID interface. Most of it is the same. You can have up to 31 devices using direct addressing and 961 devices in secondary addressing or extended addressing. But mostly no device is using this, so it's 31 devices. Okay, on the HPIL you got two actors. You got a controller and a device. You can have only one controller in a loop, and you can have up to 30 devices in a loop. So the device is a participant, and it can be a listener or a talker, and it can notify that it needs to be serviced. A controller is the one who's the loop manager. It's the one who's controlling the loop, assigning the address of each device on the loop, and saying who talks, who listens. That's basically. And you can have only one controller in the loop. Okay, listener is the roles. Listener is assigned by the controller. You can have multiple listeners in the loop at the same time. The goal of the listener is to receive data, and but you can also send command to the listener. It's called device-dependent listening command. A talker, again, is assigned by the controller. There is only one talker that can exist at the same time in a loop, and the goal of the talker is to send data, and the controller can send the device-dependent talker request to the talker. So we're going to go over that. That's the basic. This is the message. This is all the message that the HPIL implement. It's in 4 parts. You got the data message, you got command, ready, and identify. Basically, the data is to send data. That's easy. Identify is normally to check. You send and identify the loop, and it's going to detect if the loop is, you can communicate over the loop, or if the loop is broken. But also, it's a way to detect if somebody needs to be serviced. So it's an identify message. And command and ready are that's where you're gonna control the loop. You're gonna assign that you do addressing and so on. And how it works is that each frame on the loop is 11-bit. The first 3-bit choose what is being sent and how to interpret the data side. These are the 2 tables for command and message. This is all the message in the HPIL interface. There's a lot of that is not implemented. There's a lot of hole in the table that was never defined or neither implemented. Now, communication pattern, how it works. That if a controller sends a data, a ready or identify message, is sending a message to the first device. The device will interpret that message, and either is going to forward the message as is, or he's going to modify the message, or he's going to create a new message and send a new message instead. So and each one will do the same, and the same message will come back to the controller. So that's the pattern. It's going to be different for each type of message, but each message is part of either a data, a ready, or identify message. So with that, it will always be in the same pattern. On the command pattern, it's a little bit different because on the command pattern is HP assume that it's a message that's going to take time. So he's sending the command and then he's going to send another message saying, is the previous command has been completed. So how it's working is that he's sending a command and each device will right away forward the command and that will come back to the controller as fast as possible. At the same time, just after the first device is forwarding the command, he's going to process this. And he's going to check, is the command for me? And this is for him. He's going to do something. If not, he's going to do nothing. Then when it's coming back, the controller will send back another message, ready for command. And this is part of the ready group. And the ready group is will hold, and if the previous command is not finished, it's going to wait here until it's finished, and then it's going to forward the message. And when it's coming back to the controller knows that every device on the loop is ready. So that's how this is how it's working at that point. Okay, on the equipment side, in order to try that, we need at least 2 HP71B. But it could be more. I have a setup here where I have 5 71B connected together and they're talking at the same time. And everybody's seeing each other, it's working. So you need 2 or more 71Bs, HPIL interface, HPIL cable, and if you really want, you can have dual HPIL adapters and you can have multiple loop and have fun. You can have also virtual devices with the pillbox, who is converting HPIL to USB, and virtual software that you can use on a computer, virtual IL or PI IL that simulate devices. Why I'm using HP71? Because it's the most advanced HPIL controller ever created by HP. And you can have multiple HPIL. So it's you can create very complex setup.
Now, is it strictly a timing so that say loop 1 and loop 2?
If you have multiple loop, each loop is standalone.
Okay. So
the controller, the device
there's one loop and a second loop.
Yeah, but the device who has multiple HPIL can be a controller on one and a device on the other. They are completely separated, but it can do the bridge between the two. Why using a 71 instead of the 41 and the 75? The 71, the 41 and 75, I could use either of the three as a controller, but the 41 and the 75 can only be a controller. You cannot have a 41, neither a 75 as a device on the loop. It's not working. So the 71 is the only one who can do this. There's not the 71 also is different another way. On the 41 and 75, it's the main processor that's sending the message on the HPIL side. And on the 71, you have a separate I/O processor in the HPIL interface. So the 71 can be off, and the HPIL module I/O processor can do its job without ever waking up the 71. And he will wake the 71 if something more advanced needs to be done. But if you can do management stuff on the HPIL, the 71 will sleep and you will see nothing. Okay, I'm going to use two legs in the example. We're going to communicate with HPIL, and at some point we're going to use software interrupt to do this. And there's some complexity in order to set it up and use it. But for some things that we do, it's possible to have a more simpler setup. And those tools files have words that help us do these things more simpler way. But I'm going to show both. Okay. The first setup is to use the simpler setup is to use a controller and a device. That's it. And we communicate with only one device and one controller. And normally when you do testing, what I do is I add 2 pillboxes. The reason why is I'm putting a sniffer on both sides. And I can see what's coming out of here. That's going to go out here, and the pillbox goes into the virtual software. It's going to go to a virtual scope. That's going to show me all the HPIL message coming out. And then it's going to go back here. The 71 will do its thing, and that will go out. And I will capture every frame coming out of this. And it's going back into the 71B. Because sometimes a message that's going out here will be the same as this, as coming in, but often it's going to change, that what's coming out will not be the same as what's coming in. And if you only look at one side, you don't have the full story on what's going on. So that's why you need 2 pillboxes to do this. Yeah?
In order to work, you have to have software in both 71. One of them says on the track.
Why? Huh? You don't need software. You can send command from the keyboard directly, but normally you write software because you want to do more advanced.
You don't need an IL module or anything?
Yeah, but yeah, in order to do that, you have a 71B and an HPIL module in it.
And the other one also?
Sure, because we're doing HPIL communication. Okay, but in order to capture the frame when you start, you don't necessarily understand how this is working. So in a way, to understand that, you need to have sniffer to see what's going on. And the software here, you're using a software that will show you how the frame, what's going on and what's coming in.
I remember years ago, I wrote a little routine that before I did anything, I'd run that routine and it would send out 3 or 4 different commands and would prepare the loop so I knew what.
Yeah.
If I didn't do that, I was you go crazy.
Yeah, but you need to understand how the loop works.
Yeah.
And okay, the first thing, how we can communicate with 271B. We don't have peer-to-peer communication in the HPIL world. It's always a controller that gives somebody a talker and somebody a listener. And there's message going out and there's some detection going in. So the first thing we can do is to set a device status. So each device, a device is not, there are some devices that don't support status, but normally they all do. And it's the way for the controller is going to send a message and the device is going to set a status. And for some status, the controller would detect that the device has something to say to the controller. And when you set the value, it's 1 byte. It could be multiple bytes, but a 71B only support 1 byte. And the 6-bit is the service request. So if I want the controller to detect that a device wants to send a message to the controller, he's going to set that bit and a value here. And the controller will detect that it needs to be serviced and it's going to fetch the value. So that's a way for the device to warn the controller, I need to do something. I need to send you a message. Okay, so on the value here, the value it can be any value. This one, this bit is a specific bit. If it's 0, the controller will not know that you have changed the value. If you set 1 here, it's going to know it, it's going to detect it. And the value here is a value from the device or system. HP has defined some message that's global to every device, and they're here. But if you want to do your own application, normally you will always set this as a device, and you're going to put your value, and you're going to define your own value, what you need to do. Now, how this is working. The first thing you're going to do is the control on the 71B. Technically, on a machine, when you do a control on, you take control of the loop. You become the controller. And becoming a controller means you're resetting the loop, asking each device to release their addresses, and then you do the addressing. So that's control on, do that. And if you look here, what happened, what's going out from the controller and what's coming into the controller are the message that the control on will do. It's basically saying interface clear. It's saying all device, clearing your interface. If you are a talker, you're no longer the talker. If you are a listener, you're no longer a listener. And it's resetting to a known state. Then it's going to send, and since the interface clear is a command, you need to send a message are we ready for the next command? It's following the pattern that we see before. So it's sending an interface clear and ready for command. It's coming back to the controller, and then it's going to send auto address and configure. And this is a message saying to all device, and when the device is receiving that, is putting his address to 31, saying I'm not in the loop. And then it's going to start the addressing. And the controller is going to address itself to 0, insert the address 0, and it's going to send an address, a command with address 1, and each device that can be addressed will take that address, add 1, and so on. And it's coming back to the device. So that's how hpcalc initializes itself. It's clearing all the interface, resetting all the address, and redo the address. After that, everybody can talk or listen if they are allowed to. I'm going to set a request so that in the 71B was acting as a device, and I'm going to get it. How do you get that? You're going to serial pool with the address. So that in our case, the controller is going to send a serial poll with the address 1, and it's going to get the status. So I'm setting 31 in the device. I'm getting it. If I'm setting 0 in the device, the controller is going to get this, it's going to get 0. But serial poll here means all those messages. Okay, and all those messages is basically unlisten, nobody's listening, I'm going to set a talker with the device, and he's going to become a talker, and then that is sending the next one, the next command is send status. And the status will be sent. He's going to receive it, and after that, he's going to say, there is no talker, no listener anymore. So serial poll with the address mean all those messages going on the hpcalc. And this is the same that we saw in the message, but in sequence diagram, and you can see interface clear, it's a command, it's sending, it's starting to clear the interface, ready for command, are you ready? Yes. So it's the same message that we saw before, but in a sequence diagram that you can sometimes better figure it out what's going on. Same thing here, that's the serial poll, unlisten, I'm assigning the talker, send status. If some devices has more than one status, so it's going to send the status from the least significant byte to the most significant byte. And that will going on until it's the end. When it's finished, it's going to either send an ETO with the message end of transmission OK, or it's going to send an end of transmission error if there's some error at some point. But in this case, it's OK. And he's finishing with the other commands. Okay, service request. Service request in a way that you send the device, when you set the status, the device status to a value, you set the bit number 6 at 1 to be I need service. That's the one that we saw a couple of slides before. On the HPIL message, when you set the status request, the identify frame, when you send an identify, it's going to send with 0. And then when it's 0, it's identified. But if one device needs to be serviced, it's going to switch that bit to 1. And that's when it's coming back to the controller, it's going to know, because that bit has been switched to 1, that one of the devices on the loop needs to be serviced. It doesn't know who, but it knows that one of the devices is in need of service. Okay? So, and the logic is, I'm setting the device status to and the bit 6, and there's another bit in the HPIL that is setting to the same value, and on the data frame or identify frame, if the bit is set, it's going to switch that bit on the device. So that's how you detect. You set in a device, you set the status to end with the bit 6 at 1 to 1, and on the next frame, the device was going to split that bit, and when it's coming back to the controller, that's how it knows that somebody wants to talk to him. Okay, same thing here. Control on is doing the resetting the loop. I'm setting request 1. When I do setting request 1, I'm actually setting 1 in the status part, the value. I'm putting the device status service request to 0, and it's a local message. It's a device message. If I send an identified message, the number identified with 6 will keep 6 because the bit is set to 0. So the same message that's going out to the controller is going to come back to the controller. So the controller says, oh, nobody wants to talk to me. Everybody is okay. So at some point, if I'm setting 64, so I'm setting 0 and 1 here on the bit. What will happen is that I'm setting that bit, and that bit here is going to set also in the HPI interface itself another service request bit. There's like 2 service request bits to 1. And then I'm going to send an identify message. And that is going to go out on the loop at 600. And the bit will be set. The controller will receive 700 instead, with this identify and switching the bit. So the controller knows that somebody needs to be serviced. And I can send multiple time identity, and that will always return 700. So until I'm handling that device, I will continually receive at each identity frame, I need to be serviced, and so on. So I need to do something about it. Okay, how you reset that bit, or how you get, once you get the notification, how you get the data, and how you reset that bit, so you know that it's been handled, and if there's another device that needs to be handled, I can do it. So again, I'm setting 66 here. That's going to put 2 in the device status and 1 in the service request. And it's going to set in the HPIL chip, it's going to copy that value to its own IL service request. I'm setting identify. The 600 here, identify is going to become a service request. So I know that I need to do something on my side. So I'm going to do a serial poll, and it's going to go out. And I'm going to receive the value. But when I do this is asking the status of the device. The HPIL interface on the other side will reset the bit to 0. Not the device value, but the extra bit is going to be reset to 0. So when I send the next identity, since it has been serviced, he will no longer set the bit. But if I'm asking him again the value, I'm still having 66. So he has not reset the bit in the device status, but he has reset the bit into the HPIL interface itself. But the thing you need to understand is just you're going to send an entity, you're going to set the request, the device status. You sending a message in a loop, is somebody I need to be serviced? Yes. And I'm going to ask each device one after the other. In this case, we have only one. I'm asking, give me your status. And the action of asking the status means that it's been served. So it's going to reset the bit. Next time I'm sending an identity request, it's 0. So that's how a device can signal to the controller, you to come to fetch a value I need to send you. So that's one-way communication. Okay, now that's easy to do. This is easy to explain, but how the 71B can handle that? Because the I/O processor, he knows that, but the CPU of the 71B doesn't know this. This is only understood by the hpIL processor. Now, how you can transfer that information from the hpIL side to the HP71B is through a special set of other registers in the AL and through software interrupt. So you're going to set an interrupt bit here with service request message received. So you're going to create a subroutine in BASIC that will handle that message, and you're going to tell the hpIL interface, if that bit is set, the service request bit is set, call the handler routine. So that's how you handle that in the program. So what we're going to do here is basically a software that the device here will set a flag and will set a value equivalent to that flag with the service request bit. And the other one here, the controller will get that value and set the same flag at the same time. So we have a one-way communication. It's going to set the status. This one is going to send identify frame. It's going to get the value. It's going to know that it has something. There's service request bit will be set, and it's going to get the value and do set the same flag on the other side. So if I'm restarting this again, oops, you see that the two sets of flags are synchronized. There's maybe a little delay between the two, but basically they are synchronized. So how we can do this? There's three parts. There's the interface, the ISR detector that's the one that's gonna detect the service request. So it's gonna send identity message, and if there's if it's coming back as identity, nothing is done. If an identity is converted into a service request, then it's gonna raise an interrupt, and the interrupt handler will handle that. The other side here, the 71B device will set a flag and will add 64 to it to raise the service request bit. And it's going to wait 1 second. And it's going to do 1, 2, 3, 4, 1, 2, 3, 4, and on in an infinite loop. Now, on the controller side, you got I need to set up my software interrupt and have the handler here. So the handler here is basically is going to receive, is going to be called by the HPIL interface. He's going to clear his interrupt. He's going to send a serial poll to get the device status. That will reset the service request bit on the HPIL side. He's going to toggle the flag, and he's going to re-enable the interrupt on the controller side. So that's the logic. You got the interrupt handler, the one that's doing the polling, and the one setting the device of the other. And how this is translated into code. This one is very easy. This is the device. It's basically an infinite loop of 1 to 4, and if I'm toggling the flag, if it's set, I'm clearing it. If it's clear, I'm setting it. I'm going to add 64 to the flag value to raise the service request, and I'm going to wait 1 second. And I'm going to do 1 to 4, and it's going to, when it's finished, I'm going back to 20. So it's an infinite loop of 1 to 4. On the controller side, when I'm going to stop, I'm going to take control of the loop, then set it up the interrupt handler. So I'm clearing the interrupt. If there's a pending one, I'm clearing it. I'm saying the interrupt handler is at line 35. It's here, and I'm enabling the interrupt 8. That is the interrupt set up if I'm receiving a service request. Because I could have a handler that handles multiple type of interrupt. There's a bit type of interrupt that could be anything, so I could have here a very big handler that will select which interrupt and what I'm doing and so on. So, but this is a simpler version, even though it's not necessarily simple. And I have an infinite loop here. Send an entity, go to 25, and this is an infinite loop. It will never go out. Since this is talking to the HPIL module and saying to the HPIL module, there's an interrupt handler if you're receiving service request. And this part will never know that this part is being called. It's the HPIL module on the back that's going to call this. And the first thing I'm going to do is reset the interrupt, ask the device's status. I'm going to set the bit, toggle the bit here, and I'm going to re-enable the interrupt and return. That's all you do. So with this code, this is my service request generator with the flag. The other one is detecting it, get the value, and set the same flag as the other one. So we have the same pattern that we saw in the video before. So that's one way to do it, and that's the standard way with HPIL from HP. Now if I'm using the same thing here, the same logic, but with the Lex file that coming from Jean-François Garnier, who is simplifying things a bit. It's the same logic. Interrupt handler, status generator, and the one that's detecting and calling. But I'm not using here an interrupt at all. How it's implemented? We see it here. Same code here, doesn't change. But here is a lot simpler. We don't need to set up an interrupt handler. We do have something that's going to handle that service request, but we don't go through this interrupt handler. But we're using a simple word that has been defined and is returning the value 0 or 1 if the bit is set. So it's simpler and it's faster also. So it's the same logic without interrupt handler here. And the difference is that with the interrupt handler, it's taking about 55 milliseconds of latency, and with this is about 11 milliseconds of latency. So it's faster. But the interrupt way is more generic. This is only for service requests. But the interrupt way can handle all kind of other stuff, other message that this cannot do. But for what we need to do, this one is simpler, is faster. So I'm using it. Okay, here, what will happen if you look at, if I'm going too fast at the bottom side, I'm going to become desynchronized at the top. And then at some point I'm going to reach the limit, the latency of the message, of the detecting of the status and getting the information is taking too long, and the device is going faster than the controller can handle that. So there's no solution to this if we only use one-way communication. The way to solve that is to have a two-way communication. That the device is setting something and it will not do anything until the controller, anything else, until the controller is sending in, okay, I've handled your request. So we need to establish a two-way communication. How we do that? It's basically the same pattern again. We got the one here that I'm going to take with this one. It's going to send the same identity message, and it's going to, if it's receiving a service request, it's going to call a handler. The handler is the same as before, but I'm going to send a device-dependent listener to the device. And upon reception of the device, it's going to raise, I will need to set up an interrupt on the device side, that's the other way, that is going to handle that message. Now, a device-dependent listener is a way to communicate, the controller can communicate to a device. There's 32 messages possible as a listener and 32 messages possible as a talker. And those are custom for each device. If you use a tape drive, a DDL0 may mean to do rewind the tape. The other one is reset, clear the buffer, and all kinds of stuff that you send something to a device that doesn't need him to talk you back. If I want the device to send me data, I'm going to send a device-dependent talker. And the talker, the role of the talker is to send data. And the role of this listener is to receive information, okay, or trigger something. In our case, I'm defining a new message. My 71B device as a new message that is going to have to handle is the DDL0. So that's, for me, is a way to send an ACK from the controller to the device. So the device here is I'm gonna need at some point to set up an interrupt handler. And the handler is going to detect, is going to clear the interrupt, and is going to detect, did I receive DDL0? Yes. I'm going to say my request has been handled, and I can continue what needs to be done. And I'm going to re-enable the interrupt. So with this, we have a two-way communication, and we cannot go into the problem of losing the message like we did before. Into the code. Basically, what we have here on the device, okay, if we look at the controller, same thing as we had before. Control the loop, an infinite loop here, but if the service request is returning one, call the handler. The handler is getting the device status, setting the flag, but at the end, it's going to send untalk, unlisten, and it's going to ask the device to become a listener. So I'm sending the message listen 1, and I'm going to send the DDL0 and reset it, saying you're not listening. Once the message is sent, I'm resetting the listener. There's no more listener. So that's a way for the controller to send the ACK. On the controller side, now I have to set up my interrupt handler, but in this case, I'm setting an interrupt with the device-dependent message 1. Because the device is going to receive a device-dependent message this is, you can trap that with an interrupt. It's the interrupt 1. For the previous example, I was using interrupt 8. Now I'm using another software interrupt with the 1 for device-dependent message. And I have a loop here, an infinite loop, that I'm setting my flag, setting my request, and setting another variable to be 1 here that is going to loop here until it's no longer 1. Okay, so that's an infinite loop. So I'm setting the flag, setting my value with raising the service request, going to an infinite loop. Now, when the controller sends the device-dependent listener to the controller sending that to the device, is going to call, the HPL is going to call this, and going to reset the interrupt, read the device-dependent command message, and then if it's 32 to 63, it's equivalent to device-dependent 0 to 31. And if it's 0 to 31, it's device-dependent talker message. That's how it's working. So it's going to receive, if it's 32, I'm receiving a DDL 0. I'm going to clear the flag here, and I'm re-able to interrupt and returning. Now, this one is an infinite loop. But when that happens, it's changing the value here. So that means that I'm no longer through, so I'm doing next and going here. So I'm changing the state of that loop, and if it was in flag 1, it go back into flag 2, wait for the app, flag 3, and so on.
So then when you do a line on interrupt go sub, is
yeah.
that on any interrupt, or is it for a given interrupt?
Interrupt 1.
Well, but the on interrupt, when you're setting a condition on interrupt go sub, you're establishing
the entry point of the interrupt handler. But until I'm activating the interrupt, nothing happens.
Okay.
Okay, we also have other commands like off interrupt. I can have the interrupt handler, but no interrupt active.
Okay.
Okay, so nothing will happen. I could also set up a multiple interrupt. And I want to handle interrupt 1, 2, and 8. So I'm gonna do the add of the bit in order to get that. And so here I'm going to have a more complicated interrupt handler because I have to handle 3 interrupts. Yeah. The 71B has, you can only set 1 interrupt handler. So if you handle multiple interrupts, you have to handle, you have to do the switching case here and the filtering which one and how I'm handling this. Okay, so with this one, this is the basic of two-way communication, distributed communication. This is going to work. Right now it's working with only one device because here I'm only talking with one device and the device at address 1. But if the next step later on will be how we can handle if I have 2, 3, 4, 10 71B on the loop. How can I handle that? And a mix of 71B, video interface, printer, how can I detect which one is the 71B and whatever. So with this, you have the basic of the two-way communication. And you can define as many messages as you want here. DDL 0, 1, 2, 3, 4. You just need to put the handler to handle those messages. Okay, we go with multiple device. This is the basic setup right now. This is noise. This is here noise, and this is noise right now because this is only sniffer. In the case of sniffer, they have no addresses. A device can be on the loop, but have no address. It's just that he cannot talk, he cannot receive command, it's just there, taking message, sniffing this and giving that to the other and doing nothing. I could have 50 devices on the loop and only one can be addressed. Okay, so that's how sniffer works here. Okay, now if I'm complicating this a bit, on the virtual side, going here, no address. VirtualBox is there physically, but it's taking no address. It's only passing along, converting the HPIL stuff into USB, going to the virtual software. The virtual software is going to the scope, no address. The scope is going out into the virtual ion printer. That one is saying, yeah, I can be addressed. So it's going to use the address 1. And then that's going out here. The 71B will be address 2, 3, 4, and it's going to go like that. Here, floppy 5, scope, no address, going out into the 71B. So the 71 here has address 0, 2, 3, and 4. 1 is a printer, 5 is a floppy in this setup. So my goal here is to find only 71Bs in order to do peer-to-peer communication. Okay, so the same thing here. If I do control 1, control on, that's what's going to happen. I'm going to clearly interface, reset everybody who has no address, and I'm going to send a message, everybody is going to take or not an address, and it's going to be back loop, and after that, everybody has an address and can communicate if they want to. Okay, then I'm going to set on a device. Okay, is this here? I'm going to set on the device 1 a status 65 or 64 plus 1, and on the device number 3, I'm going to set another status 64 plus 3, and I'm going to send an entity message. So what will happen? All devices have the device status to 0. I'm setting 65 here and 67 here. And I'm going to send an entity message. The first here, no, there is no status, continue. As the first is going to, with the first device that has a service request bit set, is going to convert the entity into an ESR. And that's going to continue. So other will have nothing, their bit is 0, but it's not resetting the bit. The bit has been set and it's going to be stay set until it's going back to the controller. This one is going to set it, but it's already set. It's doing nothing more than the other that's had done before. So when it comes back, the controller knows that at least one of the devices needs to be serviced, but it doesn't know which one. Okay. So what needs to be done? The controller needs to send for each device a serial poll. Because he knows that which one, somebody has made a service, but he doesn't know which one. Because of that, he has no choice to go to ask each of them. He could send the first one, no. Second one, yes, I've got a service. I could send another identity right here, message. And if it's coming back to 0, it means nobody needs to be serviced anymore because this one has reset the bit. But in this case, he will return 1 because this one also set the bit and it's not been handled yet. So, but I don't know which one. And by the time I send identity, maybe this one has set the request bit. Because you have to think in parallel here because everybody is independent and can do anything at any time. So normally what you do, because you don't, you go in through each one and you polling everybody, and at the end you get the status of everybody and you know that everybody has been serviced. But you're going to send that after that another service, another identity frame, and if it's returning 0, okay. If it's returning 1, I have to redo the same thing again. It's highly inefficient. And if you want to do that, it's complicated a bit because the complication comes that I need to scan the loop, find the 71B, put those into an array so that I know their addresses, and then from that array after that, I can only poll the 71Bs. I don't want to talk with the printer and neither the disk drive. So how this is working? The logic of the controller is basically find the device, and then do what we did before. That's the same thing. So how we can find the device? First, we create an address array and a status array, because I will need an array to store all the addresses 71B, and also I need an array to store the statuses, because I don't have only one status now. I have one status per 71B. So based on that, I'm going to go in the loop, and I'm going to ask for each device their accessory ID. And if the accessory ID is 3, then it's a 71B. So for when that happens, I'm saving the address into the array. And the one thing is to the 71B is that you can define a bigger array, and if you store value at the end, you can resize the array, and you will not lose the data inside the array that's there. So at the beginning, I'm creating an array based on the number of the device of the loop. If I have 10 devices on the loop, I will create an array of 10 entries. But if I have only 371B, at the end, I will resize it to 3. So that's what I'm doing here. And after that, I'm just showing what I have. How many devices I have, how many 71B I found, and their current status.
So do you resize the array to save memory, or
yes,
speed up the time of traversing the size of number of items that are active?
Yeah, but I don't need. It's simpler that way because the size of the array determines how many 71B. So I can do a loop. I don't have to question, is this address valid in the entry? So all the other one is going to be 0 if I don't resize it.
But it's not a performance. It's not that it takes so long to traverse.
Well, you can do this. It's a performance, but mostly easier to program at the other side. Because I don't have to care the value. If I have a slot in the array used, there's a 71.
Yeah.
Okay? And then I'm doing option-based 0, so the first one, I'm saving the number, the size of the array there. So I know that when I do one for loop, I'm saying for 1, 2, the value that is 0, and it's easier. So after that, I have the detector as before, same thing, doesn't change. The handler, then now I need to find I'm going to use the array and the address that I have that on the array. So that's going to be for each 71B in 71B's address array. And I'm going to request the status, and I'm going to save that into the same place in the second array. That's going to be the same size as the first one. The first one is having the 71B addresses. The second array is having the 71B status value. So that's big. And after that, I'm sending. If the device service request is set to 1, I'm going to send a DDL message. Because remember, I need to ask if I have 371B, I may have only one that has set the bit, and the 2 other ones have not set the bit. So I need to check, okay, I cannot send blindly the DDL0. I need to only send the DDL0 when there's a request being made. So I have to check the status that I'm receiving. Is the service request bit set? Yes, I'm sending the device and the message, and that's it. So that's basically how it's handling here. And the other side doesn't change as before. The same thing. Same logic. Okay. I'm putting here a wait between 100 milliseconds and 1 second to create a symmetric message. So sometimes 171B is taking longer than the other one to create a symmetry. And then we have the same logic that's before here. I'm waiting, I'm setting the status, waiting for an infinite loop until I'm receiving a DDL message. When I'm receiving, resetting, setting the next value. It's the same as before. But here we are now, instead of having 1-to-1, I have 1-to-many.
It's been an hour.
Sorry. I'm almost finished. So that's the device. Yes, it's the device side. So interrupt handler here, okay, and DL0 handler. So that's an artificial wait state to create asymmetric stuff. On the controller side, I check here using the Lex from Jean-François to know how many devices I have on the loop, creating the array of that, going through the loop, and by addresses, checking if it's a 3, it's a 71B, saving the value into the incrementing the number of 71B found, and saving the address of it. And that's it here. I'm going to send a service request. If the value is different than 0, I'm going to go through each one, and if the service request bit is set, I'm going to send the DL0, but only for that device that has been received. And then after that here, I'm showing what I've received. I have 3 devices. The device 2 was 41, the device 3 was 80, the device 4 was 0. So I can see live who is changing what when. Okay, the last thing here that we need to find is it possible to speed up things? Instead of having a request each one, is it possible to have a setup that will, when I send an identity message, each one that needs to talk with me, I can have a filter somehow that each one will set the bit, and I will know that's only the 3rd one and the 4th one needs to be able to handling, and not the other one. And this is called parallel polling. And how you do this is basically you unconfigure the parallel the option here, and you're going to set up each device that you want to be part of the parallel group, and that can be up to 8 devices. You're going to set a bit in which one is going to send me in the data part. That's going to define if this one is sending a request, it's going to set the identity request, the C0 bit, the service request bit, but also it's going to set up the first bit here. So on the controller, when I'm going to receive the information, let's say here, the same example, bit 1, bit 2, bit 3. If I'm setting here request and here, and I'm going to send that, the entity will become, at some point here, it's saying the same, it's going to become an in-service request, and the first bit is going to be set. Now, this one is doing nothing, this one is going to set another bit here. So when it's coming back here, I know that the first and the 3rd device need to be serviced. So at that point, if I'm smart about it, I'm going to just serial poll the 1st and the 3rd. So it's more efficient. It's important when you have several devices. If you have only 1 or 2 devices, it's okay, but if you have 10, 15 devices, it's faster. But the limitation is coming from HPIB, is that you can only have 8 devices. You can only have 1 databyte. And how you set up that is basically the same as before, but now I have the parallel configurator logic to add. Okay, and how you do that is, as this previous slide, you unconfiguring the parallel bit, that you're setting up the bit to everybody that you want to listen, to warn you. And then what will happen here, same thing as before, but here, that when I'm going to send, whoops, where is it? Here. When I'm going to send, instead of sending an identity frame, I'm going to send a parallel fold frame. It's the same. It's an entity frame, but I don't want to know the service request bit. If the value is coming back to 0, nobody needs to be serviced. If it's different than 0, then I'm going to interpret each bit received, and I'm going to do something about it. And this is the code. That's the device code doesn't change a thing. It's the same. It's the same as before. It's on the controller side that's becoming a little bit more complicated. Same here as before. Find the device, find the 71B, give them an address. But here, logic is a little bit different. I'm sending a command 21, who is the parallel configure, unconfigure, and then I'm going to set it up for each device that I want to be part of the parallel group. I'm going to set for their bit. Now, I'm not going into the detail of this, but there's a command plus which bit I want to set for the specific device. And I'm using the device address to specify the bit, and I need to do some offsetting. Then I'm going to send a parallel poll. A parallel poll is an entity frame, but the difference between the service request function that I was sending before and this one is the service request function was returning to me as value only the service request bit. The parallel poll is returning me the data into the entity frame where the bit is set to which device needs to be serviced. So I'm receiving that, and then I'm going through, and for each bit, I'm checking which bit is set, and if the specific bit is set, I'm going to send a serial poll asking the status, but from the device based on this address. So and I don't need them to check if it needs to be serviced, because if the service bit was set, it needs to be serviced. So I'm sending right away the DDL0.
But each device that actually wants to be serviced is sending, in turn, when they're polled, the data.
Yeah, that's the serial poll. But now I don't need to ask each one their status. I only need
to know which ones to ask.
Exactly.
Okay.
So this is not optimization. But sure, you can have also edge case. Printer need to be serviced, and it's not part of the parallel poll. When that happens, I have no choice to send. So if I was in the production software, I would use this, but each minute I would go to the loop and ask everybody if I've received just in case.
Are you out of paper or whatever?
Yeah, things like that. So if this is the what happened, there's a bit of offset here, but you're gonna see here the value, and sometimes you got multiple bits that is set, and this is coming from the serial poll, and the value change accordingly. If you want to see more of this, I've set up at my desk 5 71B networked together, and they're all communicating, and you can see which bit and how it goes. So what next? If you want to create your own program, but you have with this the basis of two-way communication. Now the only things you need to define is what you want to do, then define a set of DDL and DDD message and status that what you want to send as message, what are commands. If you want to set data, you're going to send device-dependent DDT message, and you have to set up the handler and stuff like that, but it's based on what you have right now is the basis. You can start from this and explore and add stuff. You can have, I didn't have time, but I want to do a chat software on the 71B, and I could have done the chat and sending chat from one device to the other device, or to send a message to everybody. And this is easily implemented, it's just I didn't have time. It's just that with a set of status, DDL, and DDT, and you have a chat group set with 71B.
You gotta have blue and green chat bubbles.
No, but in the real, HP did that in the 1980s. They had a production line controlled by 71B, doing exactly that, and they had dual HPIL, and one loop for all the device, and one loop for equipment or communication with computer or other stuff. So there was one loop for synchronizing things that need to be synchronized, and all the other loop was doing their specific things. Yeah, finish.
There's when HP offers HPIL, the longest cable, I think was it 10 meters or 100 meters?
No, it's 100 meters the longest cable.
Yeah, I think I had one at one time. I know I did because we were in the hotel and we dropped the cable down from the 10th floor down to the first floor.
Yeah.
You know, we were, but if you're in a factory, I imagine you need more than 100 meters.
No, you cannot. At some point, you have to have a shield cable. You will have, even if it's a differential signal. If you put a motor, if that cable goes near a motor at some point, or whatever, this is going to have an effect.
Yeah,
but also
yeah, of course,
remember,
but
it's between any two devices. So maybe the factory floor is 400 feet long, but it's from one device to the next device.
Because
it's a loop.
Each device provides its own
amplification
repeaters.
Well, but there's a transformer at each end of the cable, so it's going to resync, not resync, but
well, it's the IL chip that's doing that. It's doing a retransmission. The transformer provides the electrical isolation.
Yeah.
It's the chip that's generating the signal.
Yeah.
But you could have 31 devices, each with a 100-meter cable between them. So you could have miles of assembly line.
Yeah, but to be honest, if you do that, at some point the communication speed will go down. So at some point it's the number of devices, but the message has to be sent, and it has to travel. Yeah. And this is not fast. It's about 5 kilobytes per second or something like that. It's not.
Yeah, but even a couple miles of cable, the speed of light delay, and even with velocity factor of say 0.6 or 0.7, it's going to be insignificant compared to the other delays that IL already has actually. So it's not really going to slow down very much.
Isn't another one of the advantages of HPIL noise immunity?
Well, it's how it was built with the differential signal, and it was the signals go to 2.5 volt to 0. There's how it's encoded, but
I think HP did recommend shielding beyond a certain length, but I don't know what that length was.
Well, I never saw a shielded cable either.
I remember, Jake. Do you remember what year we were in Chicago when who's the guy from New York? We set up all the disk drives with IL.
Mike Markov.
Mike Markov. Okay. And I remember we had a whole bunch of long cables, and we took the cables in our hotel room. We wrapped it around every electronic device for noise, and lowered it down, and we did everything we could to try to disrupt it, and it was very, very, very effective.
Okay, I just finished here. We have, this is the reference manual if you want to know more. The one that's very important is the interface specification. That's showing you all the frame, how it's working, and basically, and the HPIL introductory guide. That this is mostly a simple introduction. It's not complete at all. This is the one that you want to read. And also what's interesting is to read the this one, the 75 read IO instruction. You will see that you have number of registers in the HPIL side, and they explain each one register, what it does, and it will give you a good insight. Also, the internal design specification. I'm always inside this, understanding how this is working at the low level. So there's, with the presentation, you have a virtual floppy disk with all the programs that I've been using here, there, and a loader program. So the things, if you want to try it on a 71, if you have 271B, you just free a port 0, that's a 4K, you're gonna free RAM. You copy the tape, you do a control on, you copy the payloader from the tape into main RAM, create a free port, run the loader, it will load all the program into port 0, then you just purge it, and then when you finish, you can do a claim. And on each 7-in-1 you do this, and you run the good program with the device, the controller, and you can experiment what it does. So everything that I've been doing here, they're there.
Is the program on the controller different?
From the device, yes, but I have multiple controller program because at some point you have one-to-one, one-to-many, different by interrupt, no interrupt. I have different type of device program and controller program.
Okay,
Question?
Sylvain?
Yeah? No? Everybody's still awake? No? No,
No, I'm not awake.
sorry. Thank you.